Good morning, guys. As per syllabus, we are in the third module. Last class, we have started the topic about the electric field in the material space. It's more practical topic. And this topic, even today, we are going to discuss a lot of discrete topics which are related to the material. The only difference between this topic and the previous topic is previous topics we assume only the free space. So epsilon naught is the only term we have considered. Or we assume all this electric field, all this field, force, source, everything exists in the free space or vacuum. So if it is kept in, all this happen in some non-vacuum medium, like any other medium, then what will be the electric field? What will be the change it's supposed to undergo? All this we will study. For that, it will be classification, conductor and dielectric. Our focus will be to study both conductors and electric field, how it will it survive inside the dielectric or not, or will it survive inside the conductor or not. The dielectric medium is an insulator medium where permittivity will be greater than 1. And we are talking about the conductor. So we discussed these three different current sources: line, surface, and volume current. I, K, and Z, where K and Z represent the surface current density and Z represent the volume current density, where the unit is ampere per meter and ampere per square meter. More practical, frequently we will use this, and we need this formula to calculate the total current. You need to use this formula, I equal to Z vector dot ds vector. So the volume current density, if it is given, to calculate the total current, you need to integrate it over the surface, closed surface, or the surface area surface area through which the current is flowing or charges are moving. This we have discussed. And three types of currents exist. One is convection current. It's a current which is flowing through the vacuum, where there will be no collisions because there is no conductor, no conductivity will be involved. So there will be no term called sigma. Whereas due to the applied field, the charges or the free the electrons in the vacuum, it will be accelerated and it will flow, and we call it as current. So there will be no collision. There will be the equations will be quite simple because there is no collision. There is no collision. If you're taking conductor, as usual story you need to take, you need to consider the resistivity of the medium or conductivity of the medium. So here there will be no conductivity term, but here you need to consider the conductivity term or resistivity term. They need to be there. Finally, the displacement current, already you are aware of it, but right now we are going to discuss that will be the current which is flowing through the capacitor, or the current flow due to the changing electric field. That we will discuss toward the end of this subject. So our focus now will be about this, mostly on the conduction current, but anyhow we will start with the convection current. The convection current is the current flowing through vacuum. It doesn't require conductor. So we need to find the convection current density or the current density. To find the current density, convection current density, consider this. I can show with that already available. So assume this blue region, some rectangular region you are seeing, right? So that is the region in which the electrons are flowing. It's a free space. Electrons are moving in the y direction. Now let us calculate the current density. Let us have some equation. The current is dq by dt. The current is nothing but rate of change of flow or changing the numbers of the electron. So if we consider the current which is flowing through the, let us assume the electron cloud is passing in this direction. Now let us consider the electron cloud which is passing through this region, highlighted in red color here. Consider this region. The current is going to pass through this, but electrons are passing along the y direction at the velocity u. Now let us write the current or elemental current which is passing through that elemental area. So this small region with defined with length delta L or dl, or the surface area is delta S, and the amount of charges which is passing is rho v. It's represented with rho v. That is rho v amount of charges is flowing in the y direction. Now we are going to calculate how much such if electrons are passing, then what will be the current equation we are going to get. Q is rho s into ds. Or the total current, let's calculate the total charge. The total charge in this volume, or the small elemental volume, is the volume charge density multiplied with the volume. So the volume is delta S. I will take this representation delta instead of D. So delta S into delta L is the volume of the volume. So the total charge will be rho v multiplied with the volume. So the elemental current will be equal to delta Q by delta T, where Q is rho v, I will continue here, into delta S into delta L. Rho v is going to be constant, we can take it outside, and delta L by delta T, separate this, and the remaining is delta S, where delta L by or dl by dt is velocity. So this volume charge density is moving at a velocity of u vector along the y direction into delta S. So if you take the ratio of the current to the surface, or current passing through the surface area delta S, you will get this. You will get the equation where delta I by delta S is a ampere per square meter, or you can say it is a volume current density. So ultimately the idea in this slide is to calculate the volume current density, or ampere per square meter. So we will take some surface area, maybe this area or this area. We will just calculate what is the current volume current density which is passing through the surface area. That's why we are doing this calculation. So it will be equal to ultimately rho v. It's a function of rho v, or volume charge density, and it will be along the y direction, and it will be a function of velocity. So there is no resistivity or conductivity term. So what ultimately you need to understand is, for the convection current density, Z vector or volume current density is you forget about this slide. So volume current density due to this convection current. This derivation is not important, just I want to show you how we are getting that. Z vector is the volume of charges which is moving at velocity u vector. So if you multiply these two, you will get the total current density, volume current density. The unit is ampere per square meter. Now, same way, let us calculate the surface volume current density. Say I told, out of this line current, surface current, volume current density is more practical and useful. That's why our focus is only about the volume current density. We are maybe after some time we will look at the surface current density. For some topics we will take, but still practical application point of view, this volume current density is more practical. That's why we are taking this. Now same way, if you calculate, let us start with this, the previous equation. But now there is a change, like the velocity, like there is applied field. The applied field will push the electrons. The electrons are flowing, but electrons, as there is finite conductivity, or because of the resistivity, the electron will collide. So all this need to be put into the equation. If you put everything into the equation, then the equation is Z vector, or volume current density due to the conduction current, is sigma multiplied with E vector. See, all this where like all the related parameters are staying here. This sigma is the conductivity in Siemens, and E is the applied field. Okay, so more the field, more you will get the current. So more the better the conductivity, you will get the better conductivity. Sorry, the conduction current. So it is like a force. This is the applied force. This is the force applied, and free electrons whichever is available in the conductor, or that will be decided by the conductivity. If the conductivity is more, you will get more free electrons. So this applied force is pushing the electrons, and you are getting the current. In that way, you can understand this equation. In the previous case, in the convection, it is like rho v into velocity. Okay, so we are here actually, we assume like electrons are moving at the velocity. We assume that it is moving at some velocity. Okay, so we here we not included the force term. because as there is no collision, we will assume this will continue, it will continue the same velocity. So this equation right from now, we will frequently need to use this equation rather than the other one, because conduction current is what our focus. Maybe at the Ampere's law, while discussing, we will take the displacement current, but until that time, we will consider this equation. And this topic, whatever we are discussing today, maybe today, a lot of discrete topics. Formula is quite simple, no vector, nothing will be involved, but you will get minimum 4 mark to 6 mark. So it's easy to score, very easy to score, but you need to understand the terms, each and every term, meaning of each and every term. Now let us express now we have voltage, we have electric field. We are talking about the current. Now let us try to relate, we will try to relate electric field or field parameter and circuit parameter. Field parameters means electric field, circuit parameters means voltage, current, resistance. Or even see, I can include conductivity here, right? Sorry, conductivity, anyhow, conductivity, resistivity will be inverse. We will try to relate. So for relating that, we can take this equation, Z vector equal to sigma into E vector. Z equal to sigma E, that equation we can take. You know, electric field, the unit is volt per meter. So you can write like volts, voltage measured per length. Sigma is sigma. What about J? J is conduction current density, or sorry, so it's volume current density. Okay, the unit is ampere per meter square. So it is area, right? It is like, see, I'll write the unit here, ampere per square meter. Here it's volt per meter. Now we will try to relate the field quantity to the circuit theory quantity. So just look, you focus on these units. Again, units, this unit is Siemens. Now it is ampere per square meter, right? So let me write I over some area. Through some area the current is passing. Let me take A. Okay. So now if you rearrange this equation, voltage V by I is sigma L over E. Sorry. V by I is, yeah, correct. Is correct? Anything? V by, sorry, this term will go to the denominator, right? Denominator. Okay. L over rho U. Sigma and A, where sigma is the conductivity, the inverse is rho. So this is what the basic equation we have, rho L over A. So resistance is resistivity multiplied with the length, it depends on the length of the conductor and indirectly proportional to the surface area, cross-sectional area of the conductor. So this is how we can relate. In this way we can relate. Now the idea is, even though electric field is given, see where we have started with the field equation and we got this electric circuit theory parameters. So using these approximations like Z equal to I over A or E equal to voltage by current, maybe later like magnetic field is ampere per meter, right? It is like I over L. So by taking these approximations, you can get this quantities like resistance, voltage, current, we are able to get from these approximations. Is this clear? This slide is clear? Even further, if you take this equation, V by I, voltage by current, which is equal to R, where the numerator, if you recall this equation, now in this previous, from the electric field or from the field, we are getting the circuit quantities. Now from the circuit quantities or circuit theory approach, we will we are going to move to the field. Okay, you know this equation, potential or electric scalar potential is related to the electric field by using this equation, V equal to E vector dot dl vector. And I how will you can relate the current to the current source, like Z vector, sorry, I equal to rho V into ds, rho into ds. Okay, so if you, sorry guys, z dot ds. Okay, if you know the, sorry, it's current, right? Current. Okay, so z vector dot ds vector. Okay, so if you know where z is the surface current density. Okay, so even this equation will be useful solving the problem. So if the electric field is given and this um, volume current, sorry, this is not surface current density, this is volume current density. Be very careful. So it's ampere per square meter. The unit is ampere per square meter. It's called as volume current density because it's flowing through the volume. But it's passing through the surface area. That's why we are taking the unit ampere per square meter. So this is what the equation. Any doubts? This equation you only to memorize directly. You can write it in the exam because this basic relationship, you know this basic relationship. Just you need to recall and write. That's sufficient. Or even you can see I. There is they wrote in other way. I equal to see Z. Sorry, 1 minute. So what I wrote earlier, R equal to V over I. V is E vector dot dl vector. I is Z vector dot ds. You know Z equal to sigma E. Right? For conduction current density, Z vector is sigma E. You can even replace this. Okay, so now we can see a nice equation where it is totally a function of electric field. If you know the electric field, then we can calculate the resistance of the medium, conducting medium. It's possible. So these two equations are important. MAC for power also we can do. So this example, Z vector, this kind of examples you will get, questions you will get. Very simple examples because formula there is no way to, or this because these are straightforward. We can make it tricky. That's not possible. So Z vector is given, or this is so it is not ampere per square meter. It should be ampere per meter square. There's a mistake. So Z vector is given. You need to calculate the current passing through the surface. So I is Z vector dot ds vector. Now this problem is about what this is spherical coordinate system, and the surface area what you need to consider is the hemispherical surface with theta from 0 to 5 by 2 and phi is from 0 to 2 pi. Okay, anyhow, radius we need, right? Radius fixed here, it's given 20 meter, sorry 20 centimeters given. You can calculate this. Same way you are asked to calculate for the radius of 10 centimeter. Later you can try this. Maybe take 30 seconds or 1 minute time. Please go through this. If any questions, please ask. Other simple example related to normal, I think, let's first read. A wire of diameter, diameter is given, wire diameter is given. Sriram, what time you are entering? Welcome others to the class. 10:20 you are entering. Baumik entering now. I usually don't do this, but you guys are making me to use these such options, explore such options. Let's see who are all entering. Vinith. Vinith, I know you can hear me. Money, welcome. So whoever is entered, you will get a welcome note. So wire of radius 1 mm and conductivity is given. Number of free electrons, all this stuff, free electrons are given, number of electrons. Then what else? Electric field, applied electric field, all these details given. First, you need to calculate the charge density. Charge density of a free electrons. I'll directly show that. They can calculate the charge density. You need to multiply. In this over this volume, there are 10 power 29 electrons available. That is 10 power 29 electrons per meter cube. So the total charge density is you need to multiply with charge of or charge strength of each electron, that is minus 1.6 in 10 power minus 19 you'll get. So such basic things required. So next point is current density. Current density means if it is not specified, it is not surface or volume line, it is about the volume current density. So Z vector, so Z is sigma E. Sigma conductivity is given. See, conductivity is given. Electric field, applied electric field is given. In time we can we can calculate this. Then the current in the wire, total current in the wire. So I is current. See, these formulas you don't need to memorize. It is different. If it's open book, it's fine. Otherwise, even it's open book, it is difficult to locate these formulas. A lot of such discrete formulas will be there. So total current, you need to calculate what are the details given. Current density is given, ampere per meter square is given, and area is given. Area is, what is the area? Area is a cross-sectional area. So from the radius you can calculate, right? So phi r square. So where r equal to 0.5 mm. It's given, right? Diameter is given. So welcome Kevin George. So this way we can calculate. Then another problem. Here you need to calculate. Welcome Sudhir. Welcome Mr. Money. Sudhir is again joining. Welcome again. See, there is a lead material, a lead bar of a cross-sectional area is given. There is a hole made, and that radius, this diameter is given 1 centimeter, and you need to calculate the total resistance. So the total resistance you can calculate, and you can subtract this part. That way you can calculate. So our resistance is R equal to rho L by A. In this here, mostly it will be, instead of resistivity, conductivity will be given. So you need to take these formulas. L over conductivity times conductivity multiplied with area. Okay, so first you calculate for the entire area, then you need to subtract this area. Then next topic is continuity equation for current. Again, we will start with this equation. I is Z vector dot ds vector. You can apply the divergence theorem here. So if you apply divergence, you will get del dot. By taking del dot Z vector into dV. Same way, this right side, here we have applied the divergence theorem. In this left side, how will you relate? Check whether any equation relating current and volume. We have this equation. Which equation you can take? Can you suggest which equation? Here we need dV, right? We need dV. So what will you take? So far we have equation like I equal to Z vector dot ds vector. Any other equation? Even you can take rho v, right? Or now we don't have option, right? Then we need to look at this current. So current is dq by dt, right? Let's take this side as it is. So I is dq by dt, and when you will claim it as a current, like let us say in a volume you have some 100 number of electrons. If the 100 one after other, if the electrons are leaving from the volume, you will claim like there is a current, volume current density, or you will measure like there is a current flow. But what happens inside this volume is there will be a reduction in the number of charges. Okay, if you see the current flow passing through the surface area, then you can say there will be reduction in the number of electrons inside, right? So that's why negative sign. So minus dq by dt. Now the why we are writing this equation is we want this dv term. That's why we are doing all this. So you know q equal to rho v into dv. That's why. Okay. So in the other side you have del dot j into dv. Okay. If you compare both sides, now we can get del dot j vector equal to negative of dou v or dv by dt. What is dou rho v? Sudhir, you can join maybe in the next class. I think you are getting some severe network issue. You are keep disconnected and you are joining. Maybe you can try it later. So del dot j vector. So what you got in this previous slide is that's got deleted. So del dot j vector is minus dou rho v by dou t. What is the meaning of this divergence equation? That means divergence of j vector means the volume current leaving this j vector means volume current density. So the current density leaving the volume is equal to the rate of reduction in the total charge enclosed by the volume, enclosed by the closed surface. That's meaning of this. So continuity equation of current, meaning it's like now try to get the meaning of the continuity, or you can say this with this equation is obey the charge conservation. Okay, if you're getting current, obviously there should be a reduction in the storage. That's what. Okay, that's why minus d rho v by dt. This will lead to increase in the, or you will get the volume current density or current density. This is known as the continuity equation for current. Then one more small term, maybe two more questions you will get from this: relaxation time or rearrangement time. If assume there is a conductor and or there is some conductor or some dielectric, let us take anything, some material, let us take some conductive material. There is no current movement. If there is no current movement, then what is the formula? Then del dot j should be equal to 0. That's what the condition. Okay. Now, if you put some charge inside the material, let us put some charge. Okay. Let us take two cases. One is good conductive material, a material with better conductivity, and consider a material which has very poor conductivity. So in a good conductive material, if you put some electron somewhere, any point in the space, this volume, what will happen? This rearrangement will happen. This electron will combine with the hole, and it will this recombination, or the what will happen? Like it will settle down, right? This will recombination process will take. Okay, immediately it will be settled, because as it has like it's a conductor, it has free to move, right? It can free to move anywhere, and this recombination will happen, or equilibrium state will be reached in case of conductor material. If it is a poor conductor material, if you place some electrons, so even though it is poor conductive material, it still will have electrons, or still it can move, but it won't immediately happen, but it will take time to recombine with the, let us say, some 10 electrons I am putting inside. So don't think that these 10 electrons will stay there for all the time. It will try to recombine, and it will try to reach the equilibrium states, because we are not applying any force. So after some time it need to settle down. The recombination process will take, and it need to settle down. So in this case, that in both cases, relaxation time or some time settling time is nothing but the time taken by the electrons to settle or reach the equilibrium state. Technically speaking, If the number of electrons is reduced by to 33% of its original value, or sorry, 36.8%. Okay, let us, if you assume, if you put 100 electrons inside, after some time it will become 36.8 number of electrons. Okay, so the time taken from 100 to 36.8. So what happened in the meantime? This recombination process, or it is toward equilibrium, all these things happen. After some time, the equilibrium state will be reached and the total current will be zero, right? So this time is known as relaxation time, and this formula is sufficient. Relaxation time is directly proportional to the permittivity of the medium and directly proportional to the conductivity of the medium. So it's very clear. If you, maybe with this example you can clearly understand. You need to calculate the relaxation time for two cases. One is for quartz and distilled water. Quartz and distilled water. Distilled water, the conductivity, you see this conductivity is 0.339 into 10 power minus 5, whereas for quartz it is 2 into 10 power minus 4. Okay, as it is the denominator, you can see it is taking long time to settle. See, sorry, see in this case quartz, the value is, see denominator is, sorry, there is a mistake. I mean, let me check. Quartz, the conductivity of the quartz is 10 power minus 17, and distilled water is 10 power minus, or 10 power minus 4. Yeah, it's correct. Okay, so the quartz, you know, the distilled water we used to use in battery, right? Battery for the charges to flow from one node to another node. So the conductivity is better. So that term is in the denominator. If the conductivity is better, so as the denominator is more, then relaxation time is less. So the electrons are easily settling. They are easily flowing in the medium. That's why you can blindly say, even without calculation, the distilled water, the settling time will be lesser compared to the quartz material. Others, you are entering by 10:33. I don't know what you guys are doing for 30 minutes. I don't know why you are joining now. I think almost all the classes you guys are getting attendance, and 50% attendance is sufficient for this semester. I hope all of you will have probably 90 plus or even 99.9. Why unnecessarily you are joining, I don't understand. Next topic. So far, our focus is about the conductor. We have discussed about the current flowing through the conductor. We have terms like relaxation time, then continuity equation for current, which is important for charge conservation point of view. Then we have term for current density for convection and conduction case. So these are the topics we have discussed so far. Then let's move to the dielectric medium. Dielectric medium. Dielectric medium means like this insulating medium where the conductivity will be very poor. The medium can be called as this the dielectric medium may be called as a linear medium if CD is equal to epsilon E, right? If both are proportional, like with increase in electric field, you are getting same proportionate increase in the electric flux density, then we can say the medium is linear medium. A medium can be called as homogeneous if everywhere this permittivity is same. Let us say a medium with permittivity of 4.4. If everywhere the medium property or relative permittivity is 4.4, then we can say that medium is a homogeneous medium. And finally, the isotropic medium, if the permittivity is not changing with respect to direction, it's called as isotropic. So this is important. Homogeneous is more important. We will assume the homogeneous medium condition. That is why while defining the medium, even in this case, so here anyhow this conductivity is defined. Maybe in the further discussions, you will be given with epsilon r equal to 4 or some value will be given. So the meaning is this value is same everywhere in the medium. For simplicity, we will take homogeneous medium. If it is non-homogeneous medium, the value of permittivity will be different, and that should be that used to be defined with respect to space. with x, y, z coordinate, it will vary. That will be provided. This already the topic you all know, that is the polarization in dielectric. If you apply, you consider like a dielectric medium, positive charges at the center and the electron cloud around. If there is no electric field is applied, this will be the state. And if you apply the electric field, if you are applying electric field means assume this is the external field applied. Electric field applied externally. If you apply the external electric field, then it is like electric field means it will start from plus and it will end at minus. Okay, so this is going parallel to this medium, or it's applied on the medium. So what will happen? This negative will try to pull the positive charges. So more positive charges on one side and you will get more negative charges on the other end. So now the equilibrium is disturbed and this shape will something look like this. Like more negative charges on one end and more positive charges on other end. And this is happen at whatever we are looking at, this is at microscopic level. Maybe on atomic level. Atomic level, this will be like, let's say this is the one, in a single atom, this will be the picture. Okay, once you are applying the electric field, positive charges on one end and negative charges are aligned in other end. Okay, so it is like, we can say this is equal to dipole. Like negative charge and positive charge is separated by a small distance. Okay, you can say this is a dipole. And we know this term, this polarization, dipole moment. We used to use small letter for dipole moment. Let's use a script letter. So dipole moment is equal to q into d vector. So d vector will be from the negative charge to the positive charge. So this is for a single atom. If you take at macroscopic level in that medium, you will have like n number of such dipole moments will occur, or you will have n number of electrons. So each electron will experience a dipole moment. Each electron will equal to a dipole moment, and as if external electric field is applied, then you can say the total dipole moments over the volume is known as polarization. So the total dipole moment over the volume is called polarization. So look at the unit. Again, this unit will help you to understand, to get some, it will help you to get some physical insight. The unit of what is the unit of dipole moment? Unit of dipole moment is coulomb meter. This is coulomb. This is meter. Right. Then what should be the unit of polarization? See, this is dipole moment. Okay. So maybe from, you can put some script like k from 1 to n. If you add, you will get this total, right? So what will be the unit of polarization? Capital P is you need to use for polarization. Small letter p for dipole moment. The unit is, this is coulomb meter and denominator is meter cube, so it will be coulomb per square meter. So the observation here is that the polarization, the unit is coulomb per square meter. Already we have a quantity called electric flux density, d vector. The unit is coulomb per square meter. So what you need to understand at this stage, there is some relationship exists between this polarization and electric flux density. That's what we are going to see now. This already you are aware of. Two types of medium. One is non-polar medium or polar medium. Whatever I have discussed in the previous slide, that is non-polar medium, where there will be no such dipole moments exist before you apply the field. But there are polar mediums like hydrochloric acid and all. There will be like, they are polar molecules where there will be inherent dipole moment exist, but they will be of random direction. They will be of random direction. But once you apply this field, external field, then it will go parallel to this. So the polarization will be parallel to the applied electric field. So this is the case for polar medium. Welcome Raghav by 10:40. Now it's 10:40. Raghav, see what time you are entering. See, I used to handle, I think I'll go up to 10:50. I think you could join by 10:50, right? I don't know why you have joined 10 minutes early. Now the point is, let us define the effect relative permittivity. Relative permittivity. With this, I will close today. For this discussion, we can consider a capacitor. Capacitor with free space or vacuum. No, there is nothing filled in between these two plates. So this will be the electric field. Consider other case, you have inserted some dielectric medium in between this, epsilon r. In this case, epsilon equal to epsilon naught and epsilon r equal to 1. Now you have inserted a dielectric medium with permittivity of epsilon r. Now what will happen? Now as there is, as you have inserted some medium, so this line, like I will use red color to represent the external field. So this red refers to electric field externally applied. Now as this medium filled by, or the medium in that exists in between these two plates is a dielectric medium. So from this previous slide, we understood that when electric field is applied on the dielectric medium, a dipole moments will occur or polarization will occur. Okay, so this is what the picture like in this medium. I will just consider maybe 2 or 3. Okay, it is like this positive charge, right? So negative will tend to in this direction. So minus plus, minus plus. Okay, so in the bottom it will be plus minus. So this will be the alignment of the dipole. So obviously, see, if you take the neighboring dipole moments, it's like a plus minus, right? So this will get cancelled. This plus and minus will get cancelled, and the minus plus and all these things will get cancelled. So only thing left out will be this negative charge, more negative here, close to the plate, and there will be more positive charges close to this bottom plate. So this thing I am drawing in black color, right? That is happened in the medium, dielectric medium. So if you can draw electric field lines, right? This from plus to minus, there will be electric field. So there's internally there will be electric field in this direction. So this is electric field internal in the dielectric. You can see clearly like external applied electric field is in this downward direction, and induced electric field due to the polarization is in the opposite direction. So this will lead to reduction in the electric field. So there will be a reduction in electric field. So that reduction will be decided by the quantity epsilon r. The reduction will be by amount of epsilon r. More the value of epsilon r, much will be the like proportionally the electric field will be reduced. So this is what the idea is. Now let us write the equation for D vector. This is already we know. This for any free space. For free space you can take this. For free space D equal to epsilon naught into E vector. Now consider dielectric medium. What, like two cases we consider, right? One is the capacitor with air filled. You can take air filled capacitor, and second case is dielectric filled capacitor. So in the dielectric filled case or dielectric medium case, electric flux density will be increased by amount of the polarization. Electric flux density will be increased, right? It will be increased, and that's represented by epsilon E vector multiplied with psi E. This is known as, the psi E is known as, this term is known as susceptibility, electric susceptibility. Susceptibility means how susceptible the medium is to the applied field. If you take air, it's very difficult to polarize the air. But if you take epsilon r equal to 2 or 3, as the epsilon r value increases, it is more susceptible. If epsilon r increase, then it's more susceptible to the applied field, and you can easily polarize the medium. Okay, so epsilon E means how susceptible it is, electric susceptibilities. Okay, so you can write this equation with epsilon naught E vector into 1 plus psi E. See, this 1 plus psi E is known as relative permittivity. Or we can write D vector is epsilon naught into epsilon r into E vector. So far This is what the equation used to take. Now we have to consider this E epsilon r. Why we have considered? Because if the medium is dielectric, then the flux density will be increased by amount of epsilon r, or electric field will be decreased by amount of epsilon r. That's why we need to take this. We need to include the influence of dielectric medium in the fields. So the point here is, right from now, you need to take this equation where epsilon equal to epsilon naught into epsilon r, where epsilon is called as permittivity of the medium of the dielectric, and epsilon naught is permittivity of free space or vacuum. It is 8.854 into 10 power minus 12, and epsilon r is the relative permittivity. Relative permittivity is equal to 1 for free space or vacuum. It's not 1 plus a small value. Okay, it's greater than 1 for other dielectrics. So instead of air filled capacitor, if you even insert a paper dielectric current will be approximately approximately it will be some 5 to 7. Then you can see the permittivity will increase, then electric field decrease, then for the given value of applied value of potential. This is what I am expecting. That's ready. We have entered shortly by 10:50. And even Manikumar, Manikumar also entered by 10:50. Really happy about you guys. Instead of joining by 10:40 or 10:25 or 30, they're joining at the end. That's good. Just attendance matters. This is also appreciated.
Sir, I'm there, sir. I started in, sir, I joined by 10 o'clock only, sir. My net problem, that's why I'm.
Okay, please, I am ready to accept any genuine reasons. This all really I can't check, but please see that you are effectively using this opportunity. Okay, just for name check, you
Sorry,
should
sir.
not enter and deliver. It's fine. I accept if it is an internet issue or some issues. It's for personal reasons. I agree. You can. It's
Yes,
okay, but see that you are like future purposefully. You guys are not doing this. Okay, just for
yes, sir.
attendance.
Yes, sir. Sure, sir.
Okay. Okay. Thank you.
Okay, thank you, sir.
So relate or so right from now, instead of this will be the equation we will take. D vector equal to epsilon E vector. Maybe with this slide I will close. Just go through this example. Electric field intensity of polystyrene is 2.55. See this, whatever the cloth material, jean, all this dielectric material is 1.6, approximately 1.6. That point is very important in practical application point of view, that we will discuss in the boundary condition while discussing the boundary condition. So the electric field intensity in polystyrene filling space between the two plates of parallel phase capacitor. So voltage is given, epsilon r is given, that is filling the two plate between the gap between the two plates. Distance between the two plates is given. Then what you need to calculate? You need to calculate D. See, please don't look at this. I forgot to make the animation. So you need to start with D. Okay, if D is required, then what else? What is the only so formula we have is D equal to epsilon E. So E is not available. E is not available. It should be
No,
there.
sir, he is given.
Oh, sorry, it's E is given. See, why I'm taking this approach is, see, now if you directly look at this slide, you think like what kind of problem is this? You will think like this, nothing is there, right? But in the exam, as we have a lot of formulas, it will take time you to identify the formula. That's why what I'm telling is, first write the known quantity, then try to find the, you can recall the equations. You know, E is there, so you have this equation, you can calculate. So second, P, polarization, you need to calculate. So polarization, we have formula like sum of polarization, like density, dipole moments. What is Q into D vector over volume? This is one formula. And so that's not possible here. D is given, but the dipole moment is not given, so you can't use that. Okay, what else? P vector is one more formula I wrote in the previous slide, epsilon naught into susceptibility times what is that E vector. So E vector is available, epsilon naught is known, but susceptibility is not given. But susceptibility in the previous slide I have shown 1 plus susceptibility is epsilon r, electrical susceptibility epsilon r. So from that you can calculate epsilon r. See guys, this formula I forgot to emphasize one point. For free space, the susceptibility is 0. It is not at all susceptible to the applied electric field. Then 1 plus 0 is 1. So relative permittivity of free space is 1, or vacuum is 1, because we can't polarize the medium. It's not susceptible to the applied electric field. So other parameters calculated. Sorry, with this formula, this is not useful. Then third point, surface charge density of free charges on the plate. Surface charge density. Surface charge density rho s. Really, I think today I don't discuss any formula, but think about this rho s. Really, do you think anything you can calculate from this? You'll think you can't remember any formula, you write the unit. Coulomb per square meter. Rho s is coulomb per square meter. Now think anything is possible from this. E is given, epsilon r is given, d is given, and just we have calculated d. So usually in the problems there are a lot of subsections will be there, right? So the higher subsections will be totally depending on the what value you are calculating from the lower sections. So here already I have calculated the d vector. The d vector unit is coulomb per square meter. So I will clean this page and I will write here. So d vector is known. See this, we have not at all discussed how to calculate rho s from d vector. So rho is again coulomb per square meter. Okay, so from surface, like rho s is the surface charge density. Let us say this is the surface charges staying in some plate or surface area of A. It's defined as rho s in coulomb per square meter. So what will be the flux density? Both will be same. The flux density will be proportional to the rho s. D vector is proportional to rho s. If you don't understand, you look at the units. Okay. Now, what about the vector? What is the direction of the D vector? It should be normal to the surface. It should be normal to the surface because we are calculating like electric flux which is perpendicular to the surface. So you need to consider the flux lines leaving perpendicular to the surface. Okay, so forget about even you know it. Even you can ignore this. You can directly type D equal to rho s. This is again this particular formula or approach, or please take this formula rho s equal to d vector dot a n cap, where a n cap is the surface vector which is perpendicular to the surface. Okay, or you can take this, or you can even this will be useful in the further boundary condition related problems. Then fourth one, the surface density of polarization charge. Surface density of polarization charge. I will skip this. It's a simple, quite simple, but I don't want to get into that discussions. Okay, we won't get question based on that. So finally, potential difference between the plates. Potential. So V equal to potential difference between the plate. Maybe you can use the capacitance formula. C equal to Q by V, right? Right. So anyhow, C equal to Q by V or Q into V. So anyhow, Q by V, right? So this is not charge per applied potential. So this formula. So capacitance is not given. So this we can't use this formula. What else then? Then only option is this the like E equal to negative gradient of V, or E equal to volt per meter. Or today we have in the starting we have discussed, right? From the field, see if you can't find anything from the field parameter, then look at the units and try to understand in the circuit point of view. See, electric field is given and you are asked to calculate potential. So E is volt per meter and potential is volts. Okay, volt per meter means like between the two plates electric field is given. So the electric field is 10 kilovolt per meter. So per 1 meter length electric field is 10 kilovolt. Okay, so what is the length? What is this length? This length is given. This length or gap between the plate is given 1.5 mm. So you need to multiply with that. Okay, so V equal to electric field, that is in volt per meter, you need to multiply with the length, or in this case it is, we call it as distance between the plates, d, in meters. Okay, that's why we will get volt. The results will be in terms of volts. So such formulas, you can have n number of such formulas. Really what you need to understand from today's discussion is electric field, volts per length, and electric flux, coulomb per area. Okay, instead of writing coulomb per square meter, if you recall, like it's coulomb per or charge per area. If you are asked to calculate charge, provided that area is provided, then you can calculate D. Okay, same way potential is given, length is given, you can calculate electric field, or anything can be calculated. So please use this circuit theory approach and look at this units of the each and every variable, so that you can find the unknown parameters from the known things. Questions? Sorry, today I took 5 minutes extra because a lot of distractions today. I have shared the attendance link. You can click the link and you can leave. If any questions, please stay. Please register your attendance in the link provided.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Hello, sir.
Yeah, yes.
Sir, I have a question regarding CAT papers. Like, I have doubt.
Yeah, please. Yeah, please.
Can you share the answer key, or like, can you?
Yeah, can you wait for a minute?
Yes.
Let others, if anybody else has, maybe I can. Even I can answer others. Which question?
First question.
Wait. May I know who is waiting?
Sir, Ashwin.
Ashwin, 1 minute. Ashwin, right? Ashwin.
Yes, sir.
Okay. Yeah, tell me. Please know this question. Which question? Two sets. Whether this question or another question?
Not this one, sir. It was in spherical coordinates.
Oh, okay. 1 moment. I'll stop the recording.